Hello, and welcome to another episode of Risky Business. Today, we're going to be continuing where we left off. We were looking at this local interrupts demo, and Banana the Monkey hopefully clarified what's going on here. We're shifting this 1 by this specific amount, and the reason we have IRQM local set to 16, right, is because that's offsetting it by an entire 16 bits. So everything, like the lower 16 bits, are reserved for something else. And then we saw the specific interrupt values here. So we're using the 3 through 7. These are the ones we're setting. But anyway, that's how that works. So this gives you the 32-bit mask, and like I say, it's, as Banana pointed out, it's a 32-bit field where the lower 16 bits are reserved. And he says probably local interrupts. That's probably correct. I don't know. I don't have Arty documentation on hand. I have the Arty dev kit linked, as well as another FPGA on the hardware section of links.risky.tv, but I don't have any documentation on it open. So, but yeah. So we know what all this is doing now, and let me see, what else do we have? So we have the enabled local interrupts, the disabled local interrupts, the entry point. Did we see where the entry point is called though? Oh yeah, it's set as the interrupt for IRQMsoft, and the timer interrupt is being set to MTI ISR. Okay. So what happens is when we get a software interrupt, the this interrupt handler fires, and it prints that we're debouncing, and it clears the software interrupt. When the timer interrupt fires, it disables the timer interrupt because the debounce logic sets it, which we saw earlier, and it enables local interrupts again because the when we debounce, we disable local interrupts. And I don't know why this is called debouncing, by the way. If anyone knows why the terminology here is debouncing, I would love to know, because I have no reference point here. I don't know why it's called debouncing, but we know what it's doing. So that's really all that matters. Because the metal actually physically bounces. I have a feeling you're joking there, RISCY-V. Before making permanent electrical contact, is that true, or are you joking? I thought this was all solid state stuff. If metal actually physically bounces, so it's not like there's hardware in this that's not solid state, or is it still considered solid state even though there's some physical bouncing happening? See, I'm not a hardware guy, so I just have to take your word for it. But anyway, it is debouncing, apparently. So yeah, so this all makes sense. And then the other interrupts we set are when the buttons and the switch are pressed. Oh, right. You're talking about the buttons. That makes sense. That the button would, yeah. Okay. I get it now. Yeah. A button is not a solid piece of metal. It has two faces that make contact. Yeah, that's obvious. I wasn't thinking about the buttons, and I was like, what's this all about? But yeah, that makes perfect sense now. Thank you for clarifying. Okay, and that makes sense why there's this whole debouncing thing too. Why it needs um, to disable interrupts and wait for a little bit because like the physical time of the button press, right? But if you were to like actually mash buttons, you can totally mash buttons faster than half a second at a time. I suppose for this it makes fine sense. So, okay, Banana says a 0.5 seconds debouncer makes sure it has the same state continuously for half a second before it takes that value. Okay. But again, is the point of the debouncer because of like the timing of actually physically pressing a button? Like what I'm wondering is why do we need it to have the same state continuously for a certain amount of time before it takes on the new value? So RISCY-V says yes, it is to account for the timing involved with actually like the physical press of the button. Point 0.5 seconds, like half a second, seems really generous for that. I suppose it's totally reasonable for like what they're doing here, but like a controller, for example, like a game controller, I know in like Super Nintendo games, there are people that do like frame perfect tricks where like they need to be continuously mashing at like 60 hertz to do like frame after frame perfect input. Uh, like I don't know if you can find this on YouTube, but if you've ever if you ever watch like A Link to the Past speedruns, specifically this guy named Andy, he can do this thing called hovering. Uh, um, yeah, I don't know if you can find like yeah, hovering the hammer bridge. Uh, if you can mash at 60 hertz, you can actually make Link in that game hover over a pit that he's supposed to fall into. And so if you're actually mashing at 60 hertz and you're getting those frame perfect inputs, it's supposed to be like it's the kind of thing that you'd see in a tool assisted speedrun where like you use a tool to go frame by frame and then it plays back the inputs. Um, but like humans can actually do this. Humans can actually do this kind of thing here. And maybe I'm being too generous. Maybe it's not totally like 60 hertz every frame, but I think it's pretty crazy like that. So yeah, that. Yeah, RISCY-V says it doesn't need half a second, obviously, and Banana says so you have to hold the button for at least half a second for it to recognize in this case. Yeah, so that makes perfect sense. Yeah, and then also just as a unrelated thing, if you're interested in this kind of thing, totally check out Link to the Past speedruns because they're awesome. If you enjoy that sort of thing. But tangent aside, let's get back to studying the code here. So, um, Okay, so we saw the enable and disable, and we understand the whole concept of debouncing now. Let's see here. So yeah, this is the timer interrupt. And then, of course, the actual interrupts for the different buttons in the switch. It also talks about priority here, that the buttons have higher priority than the switch. And I'm wondering, is that something that we set up, or is that like inherent with the hardware? Note the priority of the interrupt sources, and it says switch 3, the buttons have higher priority. So let's keep reading here. So to review the debounce again, we set up the timer, we disabled the local interrupts, and this is just acting kind of like a mutex or something, right? Like it's just indicating that you're debouncing. Okay, so then we enable the timer, of course, and we saw in the timer interrupt how this gets handled once the timer goes off. Here we're configuring the LEDs. We already saw that stuff before. So yeah, we're setting all these. We haven't looked at all these constants, but they're self-explanatory. We know that these constants are like 3, 4, 5, 6, 7. And we know we have 32, like a table of 32 interrupts here. And so it's setting the appropriate location, of course, based on these constants. So yeah, the IRQ local was the 16. So that's straightforward, the indexing that's happening here. And then the ones we didn't see were the soft and the timer. Let's see here. Probably not in this file. Where would that be? It's in an encoding.h. That one's defined to be 3. And then timer. Timer is defined to be 7. So we're setting in the table like index 3, index 7, 16 plus 3, 16 plus 4, and so on and so forth. Then we enable the interrupts. We start debouncing as 0, so that it's not debouncing. They enable the software interrupts, the global interrupts, and then of course just the loop that handles if it's debouncing, fire a software interrupt, and then set debouncing back to false. So yeah, I think we understand everything in this code now. The only thing I don't understand is what they're talking about in terms of the different priorities, because we're not explicitly setting priorities on these interrupts. So it must be like an intrinsic part of the hardware that these have different priorities. But again, I would need to like crack open a Arty dev kit like specification to find that information. And I don't have an Arty dev kit, and I don't currently have the spec open for it. We could easily look it up, but I'm not super interested in that right now. We might come back to it if I ever get an Arty dev kit. Let's just look how expensive are those things. If I ever get one, we'll definitely come back to this demo and try it on the actual Arty dev kit and look at the documentation for it, the specs and stuff. So it looks like it's around $100. There are two different parts listed here, but they're both like $100. But yeah, it's like $100 kit basically. So I probably won't be getting that anytime soon. I could put that, that's another thing that I've changed about my Twitch channel recently. If you go to twitch.risky.tv, which the Twitch viewers, of course, are already on, you'll see here that I have, when it loads, I added new links in the thing below it. I'm still working on like fleshing out how I want the stuff, the panels as they call them, to look on my Twitch page. But I did set up some stuff. So first of all, I want to show you guys, I set up when people follow me, donate or host me on Twitch, I should have like notifications or alerts as they call them. I'm using Streamlabs, so I can test them here, and I'll just show you what I have set up. So this is what happens when someone follows me while I'm streaming. Let me click that again. It's not showing up. Why is that not working? I have alert box on here. That's okay. Apparently that's not working right now. I'll look into that later. But yeah, I set up alerts. I don't know why that's not working right now. But I also set up a donate thing. So normally I advertise, the Patreon as the way to contribute if you want to financially support me. But I also have a donate thing now. And there is not a lot to it right now, but it has like a wish list thing. I'll put the Arty dev kit on there if anyone ever wants to donate $100, which is a lot of money, but if someone wanted to, I'll put the Arty dev kit on here. The other one I have right now is a treadmill, which is ridiculous too, of course. That's like $1,000, so I don't expect anyone to do that, of course, but that's the only thing I put on here right now. I'm going to put more reasonable items on the wish list. I just haven't gotten around to doing that yet. But this is another way for people to contribute financially to my series. Yeah, I don't know why the alerts didn't work though. That kind of bugs me. that didn't work. But yeah, I'll resist the urge to debug that right now. We're going to continue studying. So I think we've studied everything there is to study about this demo. I'm pretty sure we understand everything about how it works. I really need to not scroll like that. That's not the proper way to scroll in Vim. But yeah, I think we understand everything about this demo. And I just want to see if we make it and try to upload it, it should fail with that error message because we're on a Hi5 not an Arty. So local interrupts. Oh, there we go. So it doesn't even compile because it's set up to look for the Hi5 stuff. And okay, and we do see it here. Only supported for Corplex IP eval kits. So yeah. Oh, I suppose if you set the board in the build line, it would know what you want. So rather than doing Freedom E300 Hi5, you would do Corplex IP. What was it? Corplex IP E31 Arty. E31 Arty. Something like that, right? Yeah, see, then it actually builds. But of course, I can't upload this to a Hi5. Or maybe you could upload it. I guess technically you could upload it, it just wouldn't work. Because you don't have the buttons or the switch. But anyway, let's move on to the next demo. So let's take a look at global interrupts. So again, same deal here. Okay, so we have the PLIC instance T, and we saw this before. It's the PLIC driver. And we looked at the PLIC driver in detail earlier on in the series, so that's nothing new. We have a flag for state. It says switch 1 wins is the name for the flag. Okay. We have the debounce counter. So it's interesting they call it a counter this time. So maybe we can have multiple buttons pressed at once with this thing, as opposed to the last one. The counter, like the fact that they say in the comments that it's a counter suggests to me that it counts the number of buttons being pressed in flight, so to speak. I could be wrong, but that's just what I'm thinking when I see that comment. And it says PWM can't go slow enough. Interesting. Okay, so structures for registering different interrupt handlers. Yeah, we saw that before. There we have the local interrupt table again. Okay, and then we have the global external interrupt handlers. Okay, and then we have set timer. So it's setting it for 10 seconds. Okay, and then here we have the timer interrupt handler. It says if switch 1 wins, giving switch 1 priority for 10 seconds. So that's what we saw in the set timer, 10 seconds. It says all other things being equal, lower IDs have higher priority. Okay. So without mucking around with setting priority stuff, lower IDs have higher priority. So that's apparently what we were seeing before when in the local interrupt demo, it said how the switch 3 had higher priority than the buttons, right? And that makes sense if by default the priority is based on ID number. The switch came before the buttons. So of course that would have priority over the buttons. But here we're actually setting priority. So now we're using switch 1 rather than switch 3. And so we're setting switch 1 to priority 2. And it's saying giving these equal priority by setting switch 1 to priority 2. So they're setting the priority 2 here for switch 2. And in this setup, because they're given equal priority, the one with the lower ID will take precedence. So switch 1 will take precedence over switch 2. Okay, and then if we are on the other branch here, if switch 1 does not win, so to speak, we take this path, giving switch 2 priority. So here, okay, this is why we're doing this then. When we take this path, we're actually increasing switch 2 priority for 10 seconds. So now switch 2 will win over switch 1 because it has higher priority. Okay, that makes perfect sense. And then we do G switch 1 wins. I'm already rusty. This has got to be not equals, right? Or exclusive OR equals 0x1. So I mean, we're just flipping that bit. So we're flipping a bit, and we're setting a timer for the 10 seconds. Okay, so that makes sense. Entry points. So we PLIC claim interrupt, which gives us the interrupt number. If interrupt number is greater than or equal to 1 and interrupt number is less than PLIC num interrupts, so that's checking that it's in bounds, of course. It does the interrupt handler. So yeah, that makes sense. And again, we've already seen how this stuff works. It's been quite a while, so I'm a little rusty, but I believe I'm following this. I don't remember what interrupt 0 was hardwired for. I think it's like a no interrupt thing. But anyway, this makes sense. We are indexing with the interrupt number into the table of the global interrupts. and then executing that interrupt. Otherwise, we exit with the error code of 1 plus the interrupt number. Okay. And then we do PLIC complete interrupts, passing the PLIC's driver state thing and the interrupt number. And we might want to do a little review of PLIC, but we've seen how all that stuff works before. So there's nothing new there. And then we have instructions message. So switches 1 and 2 are enabled as external global interrupts. They don't go through the PLIC. You can observe priorities. Priorities invert every few seconds, which is driven by the PWM0 global interrupt. So yeah, we already kind of understood that behavior from reading the code. We have the print instructions to write that message out. We have some error handlers here. Invalid global ISR. So this says unexpected global interrupt if you get an invalid. Okay. And same thing for local. Then we have the switch 1 handler. So that does the debounce. It sets a green LED and it prints that switch 1 is on. Even if switch 2 is on, switch 1 must have higher priority right now. And then for switch 2, it prints switch 2 is on. Even if switch 1 is on, switch 2 must have higher priority right now. And it sets the red LED and does the debounce. So this is pretty similar to the local interrupt stuff that we saw before. Now we have PWM0 handler. We're using PWM0 as a timer interrupt for debouncing. So this is interesting that they're using the PWM this time as the timer, whereas last time we just used the timer, like the timer interrupt thing. That just uses that clock that we saw before. So we say if we're done debouncing, print done debouncing. Set the threshold. So it lowers the threshold these switches can hit. Clear the PWM interrupt. Otherwise, it keeps waiting, so it lowers the debounce count by 1. So this is what they were talking about the PWM not being able to go slow enough and using the count. This is why they're using the debounce value as a counter. So while they're waiting, they decremented each cycle. So they set the config to one shot, 0 compare, 0x7, and sticky, and we might want to look those up in the documentation in a little bit. But it says it clears out the interrupt and rearms the timer. Okay. And then here we have debounce. So again, that's the one thing that I guess I didn't understand about the last demo, and I kind of forgot about it until now. The fact that it has this signature right here of taking in a local interrupt number, but we're not using that. Like, we're just calling it with no arguments. And apparently that's legal in C, I guess. And the argument isn't used in the function, so it doesn't matter. But that's something to note. I didn't know that was like legal to do in C. I thought you had to pass the arguments. but whatever. So then we set the threshold high enough that these switches won't cause the interrupt to fire. Only the PWM or timer interrupts. Okay, so because we had those interrupts set to 2, we're setting the threshold to 4, so only the PWM and timer interrupts will fire. That's the reasoning there. And so when we were setting the threshold to 1 earlier with PWM0 handler, that's setting it, because the threshold is 2 to 3 for those other interrupts, they'll be able to fire because the threshold is only 1. Okay, so I think that makes sense. And okay, so I was looking at debounce. It prints that you're starting a debounce. It sets the debounce to 600, so it's just using that as like a timer, basically a time waster, because it's going to cycle in that busy loop as we saw, decrementing it once each cycle. So it's burning 600 cycles basically. So we do the same thing where we clear out the interrupt and rearm the timer. We set the threshold high enough. Yeah, so that's what we saw. Okay, and then we go to main. So here's our actual entry point. So we start out by looping over all the global external interrupt handlers and setting them to invalid, the invalid interrupt handler. Okay. Then we set the ones we actually care about, the PWM0 to the PWM0 handler, and switch 1 and switch 2. And for the locals, we set those all to invalid, but then we set one for the timer and one for the MEI. Like, that's software interrupts, right? Just normal software interrupts, I believe. It prints the instructions, or it's external interrupts. Oh, good night, RISCY-V. Thank you for tuning in. We set RGB LEDs for a visual. So we've seen that plenty of times already. Here we do the PLIC init, and again, this is from the PLIC driver that we saw quite a while back. And then we set it up so that switch 1 and switch 2 have equal priority of 2. So first of all, we enable these interrupts, PWM0, software 1 and software 2, or I mean switch 1 and switch 2. So the two switches in the PWM. It says PWM always beats the switches because we use it as a debouncer, and we lower the threshold to do so. So here we see it's lowering the threshold down to 0 so that it will always beat the switches for PWM. They set the values for the LEDs to control the brightness of it. What else? We set the priority for the PWM0. They're having the base for the interrupt, and then the offset is just 0. But they're setting the priority to 5. Okay. Oh, right. higher threshold beats, like higher threshold, or I mean priority, higher priority beats the other ones. So that's what they were talking about. They cleared the config register for the PWM 0 to 0. It says we lower the threshold. I don't know if there's like a threshold in the config register, but regardless, what we're doing is we're setting the priority high so that it will always beat the other ones because of the high priority. Okay. Then we set the do set timer. It says it sets up the machine timer interrupt. Every few seconds it will invert the switch priorities. Okay, so we already saw that. Enable timer interrupts. Yeah. Enable global interrupts. Yeah. And again, that's what the MIE was, the external interrupts, meaning the global interrupts. It sets the switch one wins. Oh, okay, so now I understand why it's called switch one wins too, because it's this demo is all about showing the priority between the two switches on this thing. So like the whole point of the demo is it toggles back and forth between priorities for the two switches. So you can play with the two switches on the Arty Dev Kit and see how the priority is going back and forth between the two. That would be a really fun demo to play around with if we get an Arty Dev Kit at some point. So then we enable all the interrupts. And while one, we just do ASM WFI. WFI. So that would be a RISC-V instruction, wouldn't it? Because this is RISC-V code. So let me get out my my reference card. WFI. Maybe I didn't skim over it enough, but I didn't see WFI on the reference card. Let's consult the documentation. Okay, I've got a lot of crap open, so let me close some stuff. We can close this for now. We can close this, we can close this. I'll close this. We can close all those Google tabs. I'll close this, and this, and this, and this. I'm gonna leave that one open. I'll leave this open. Yeah, I'll close this. I'll close this. Okay, so now we've got all our guides open again. So it looks like we don't have WFI in the user level ISA. Let's check the privileged architecture then. Wait for interrupts. Okay. So that makes sense that we'd be doing that. The wait for interrupt instruction provides a hint to the implementation that the current hardware thread can be stalled until an interrupt might need servicing. Execution of the WFI instruction can also be used to inform the hardware platform that suitable interrupts should preferentially be routed to this hardware thread. WFI is available in all of the supported SH and M privilege modes, and optionally available to user mode for implementations that support user mode interrupts. Okay. If an enabled interrupt is present or later becomes present while the hardware thread is stalled, the interrupt exception will be taken on the following instruction. That is, execution resumes in the trap handler, and MEPC equals PC plus 4. Okay. The following instruction takes the interrupt exception and trap so that a simple return from the trap handler will execute code after the WFI instruction. Okay. The WFI instruction is just a hint, and a legal implementation is to implement WFI as a no-op. If the implementation does not stall the hardware thread on execution of the instruction, then the interrupt will be taken on some instruction in the idle loop containing the WFI, and on a simple return from the handler, the idle loop will resume execution. So that's pretty straightforward. We have removed the earlier requirement that implementations ignore the RS1 and RD fields, so non-zero values in these fields should now raise illegal instruction exceptions. Okay. Interesting. The WFI instruction can also be executed when interrupts are disabled. The operation of WFI must be unaffected by the global interrupt bits in M status. That is, the hardware thread must resume if a locally enabled interrupt becomes pending, but should honor the individual interrupt enables. For example, the timer implementation should avoid resuming the hardware thread if the interrupt is pending but not individually enabled. WFI is also required to resume execution for locally enabled interrupts pending at any privilege level, regardless of the global interrupt enable at each privilege level. If the event that causes the hardware thread to resume execution does not cause an interrupt to be taken, execution will resume at PC plus 4, and software must determine what action to take, including looping back to repeat the WFI if there was no actionable event. And of course that's what we're doing, where we have just a busy loop while one. By allowing wake up when interrupts are disabled, an alternate entry point to an interrupt handler can be called that does not require saving the current context, as the current context can be saved or discarded before the WFI is executed. as implementations are free to implement WFI as a no-op, software must explicitly check for any relevant pending but disabled interrupts in the code following a WFI, and should loop back to the WFI if no suitable interrupt was detected. The MIP, HIP, SIP, or UIP registers can be interrogated to determine the presence of any interrupts in machine, hypervisor, supervisor, or user mode, respectively. So I guess we're not doing this because we're explicitly setting up that these interrupts are enabled or disabled, respectively. The operation of WFI is unaffected by the delegation register settings. WFI is defined so that an implementation, defined so that an implementation can trap into a higher privilege mode either immediately on encountering the WFI or after some interval to initiate a machine mode transition to a lower power state, for example. Okay. The same wait for events template might be used for possible future extensions that wait on memory locations changing or message arrival. That's interesting. So they've really designed this instruction to be kind of extended in the future, potentially. Thinking ahead. So that's a really cool instruction. I'm very glad we looked at this demo, if nothing else, just to see the wait for instruction thing. That's really cool. So yeah, I mean, it's pretty straightforward. This is just saying this hardware thread can sleep until there's an interrupt. It can be idle. But the implementation doesn't have to do that. It can just be a no-op. But that's really cool. Okay, so I think we pretty much understand everything in this now. I mean, like, we probably want to review PW or PLIC stuff a little bit and PWM stuff a little bit, but we pretty much understand everything that's going on here. So let me just scroll back up here and see. I'm looking for stuff right now that we want to review. It's interesting also that we're using this timer right here for the 10 seconds between switching priorities. But then we also use the PWM. So I guess that makes sense that we use the PWM for debouncing because this timer is already tied up doing this work, right? It's busy timing for the switching priorities. But we need another timer for the interrupt stuff, for the debouncing. So we use the PWM for that. That makes sense. Okay, so yeah, this is the thing that I really want to review, I guess. The PWM config register. We're setting one shot, zero compare 0x7, and config sticky. So I want to see those bits and review what they do, basically. Okay, so where was the PWM stuff? I think it was this document here. There's the PLIC stuff. Maybe this one doesn't have PWM stuff. Oh, it's right here. This one was already on it. All right. Okay, so here's the config register layout, and here we see the one-shot bit. So we're setting that. We're setting zero compare. I think we're setting sticky. Yeah, one shot, zero compare, sticky, and 0x7. So that would mean the bottom 3 bits, right? That's setting the PWM scale. That's what that's doing. That makes sense because we want it to go as low as possible, right? So we're scaling it to be as low as possible, dividing it as much as possible. So I think I follow why we're doing 0x7 there, because that's the max you can scale by, right? Because it's 0 to 3. Or wait, that's 4 bits, 0 to 3. Whereas 0x7, that's 3 bits of scaling. Regardless, that's what it's doing, right? It's scaling. And so we're also doing one shot, zero compare, and sticky. So let's start looking at those. With one shot, the counter can increment, but PWM one shot is reset to 0 once the counter resets, disabling further counting. So it's the name is self-explanatory. It goes one shot and then it stops. Yeah, so it generates a single PWM cycle, then stops. That makes sense. And that is what you'd want it to do for a debounce. So yeah, that makes perfect sense. The zero compare and the sticky. I remember the zero compare, like we've looked at that before, but we haven't looked at the sticky one before. So the sticky bit has to do with the Deglitch and Sticky circuitry. The PWM sticky bit will disallow the PWM compare XIP registers from clearing if they're already set, and is used to ensure interrupts are seen from the PWM compare XIP bits. Okay, so it's ensuring the interrupts will be seen. I still don't fully follow the specifics of why the Deglitch circuitry is necessary and the sticky stuff. But basically, it's just disallowing these registers from clearing if they're already set, which ensures interrupts are seen from those bits. And the zero compare. So when the scaled PWM counter reaches or exceeds PWM compare 0, PWM count is cleared to 0, and the current PWM cycle is completed. Otherwise, the counter is allowed to wrap around. And then let's look at the scaling field as well. Right, so we have a 16-bit counter. Held in a 32-bit register though. So yeah, it's the PWM counter is reset when the scaled counter reaches the value, but I'm going to review the scaled counter, the scaling that happens. Okay, here we go. It's 4-bit PWM scale field. It's the bit position within the PWM count register. So 0 means no scaling. Maximum value of 15, which would divide the clock rate by 2 to the 15th. So we're dividing it by 2 to the 7th. So we should be able to figure out the speed that that's going to set it to, right? I seem to remember that you can feed the PWM off multiple clocks, right? Or maybe it can only be fed off the 16 megahertz. I'm not sure. I need to review that more. But if we're running off the 16 megahertz, then it would be 16 megahertz divided by 2 to the 7th would give you the hertz of the thing. But then we also need to know the value for PWM compare 0 as well. To know how many cycles it's going to run at that speed. I also forgot to do the start thing again. When did I start this episode? Okay, so we did an hour episode from like 1930-ish to 2030-ish. So we're probably over an hour again, aren't we? I just want to look at this a little bit more. Okay, here we go. So we're setting compare 0 to 0xFE. So, I mean, we're running for 0xFE cycles when we do a one shot of whatever the clock rate is that we're feeding the PWM with, divided by 2 to the 7th, and for 0xFE cycles. That's how long the PWM is going to last for the debounce. So I do want to figure out the exact value there, but I think that's going to have to wait for another day, since I believe we're out of time for this episode. And the other interesting thing about that is, like for the debounce, we're just looping for like 600 iterations right here before it finishes debouncing. Or rather, this clears and rearms the timer, right? So it's every time a cycle of the PWM completes. Every time we run through those, like a single cycle of the PWM, because it's one shot, it does that, and then it fires a PWM interrupt. It lowers the debounce count and then rearms the timer. So it waits that long, lowers the debounce count, and just keeps doing that until the debounce count hits 0. Okay. So it's starting to make more sense there. But like I say, we're going to continue studying this in another episode. So thank you everyone who tuned in tonight. And thank you everyone who watches on the YouTube archive, which is available at RISCY.tv. And you can follow me at HMN_RISCY to get updates about the series. Thank you also to everyone who supports me on Patreon. That makes the series possible. If you would like to support me on Patreon, you can do so at patreon.risky.tv. I will see you in the next episode, and stay risky, everyone.